Last video I forgot to do a couple little things here, so I want to go ahead and add them on. Still talking about this radioactive decay. The first thing is decay equations. You may see something that looks like this on a question given to you. And then they would do something like maybe something like that. And you have to look at this and you have to figure out what happened here. Well, if you look at this, this right here basically tells you the number of protons in this nucleus. This is the total number of protons and neutrons. And there are 12 protons here. But then after our decay happens, we only have 11 protons left. So if you think back to the different types of decays we talked about, this can only be one specific kind. It has to be a beta decay because we have dropped down and lost one proton but without losing anything else from the nucleus. We still have the same number total of protons and neutrons. So right here we've got to have some kind of beta particle. And then this beta particle, if we look at this, we have to conserve charge. Now we lost a charge here. We went down one proton, which means this has to actually have a positive charge. So we'd have a little +1 here, and then a 0 up there, because this is essentially an electron. You might actually see this reaction sometimes written where in place of that they just put a little lowercase e with a plus. And that's just for a positron. It has a positively charged electron, which is just the anti-electron. And then we have to conserve the extra bit of momentum that was missing, and we need that little neutral guy, the little neutral neutrino, and the actual regular neutrino. Here we've got the anti-electron, so we'd need the just regular neutrino to go along with this. And then we would have completed it by filling those things in. And then you should be able to add these all up, you know, the 1, the 11, that gives us the 12. So we're conserving charge in this, and we're conserving momentum by adding this in. And that's pretty much that for an example. I'll give you one more example because it might be something a little different because you just don't know what they'll actually give you. So maybe it was something like this, and then they left it blank, and then they showed you this. My last line's a little crookedy, but sorry about that. I'm going to have this little line above it. So this would be the antineutrino, and this would be just a regular electron, which also could just be written as E minus for the regular electron. Remember that lowercase e is the fundamental charge. So with just a plus or a minus just tells you it's, you know, negative fundamental charge, which is an electron, positive fundamental charge here. And you'd have to figure out, well, what would go here? If you look at this, we lost a negative charge out of the nucleus. So if we lost a negative charge out of the nucleus, what would have to happen? Well, essentially we need something added into the nucleus that would cancel it out, because we can't just gain a negative charge. We can't really add a negative charge here. We've got to just, or subtract a negative charge, I mean, from here, because there are no negative charges to subtract. So we have to basically increase the number of positive charges we have. So this would become a 7. We would increase the total number of protons that we have, and this would stay at 14 because we didn't lose any of those. And then you'd have to look on your periodic table and see, well, what's one proton higher than carbon? There you go. And that would be that. The other thing that I wanted to go over real quick was just absorption of these 3 different types of decay. So first off, for alpha, which Greek letter alpha we use to denote, this can be absorbed by just a sheet of paper. So what does it take to absorb this? Just a sheet of paper, a single sheet of paper. You have to kind of know, this kind of gives you an idea of, you know, how difficult these things are to stop. For an alpha particle, sheet of paper. For a beta particle, beta emission, you just need a few millimeters of aluminum. And then for the really bad one, the one that gives you cancer and really damages your DNA and all that kind of stuff, is your gamma. And that's the Greek letter gamma. And for that one, you need like 10 centimeters around, so about 10 centimeters of lead. In fact, you can make your career around stopping this little guy here in medical physics. You can go and you actually are the person whenever they're putting in new equipment in hospitals and things like that that have a lot of radiation coming from them. They hire companies to come in and design how much lead they need to put in the walls and all that kind of stuff. And you have to sit there and figure out how much radiation has come off, how much lead do we need. There's even some gamma absorbing like special concretes that have, I believe they have lead mixed in them. I'm not 100% sure. They have something mixed in them, helps them absorb this kind of stuff. So you can basically make a whole career out of this last one because that stuff's so bad, and a lot of our equipment will produce bad radiations like that. And you'll have to stop it and absorb it and all the different kinds of radiations that may come out of it. Okay, that was all.